Welcome to my pitch for the Generation 4 research competition. My name is Lauren Bailey, and I'm a PhD student at the University of Tennessee, and my work focuses on framework development for the integration of component digital twins for advanced reactors. Now let's start with, what is a digital twin? Well, it's a virtual representation of a physical system that is then connected to that physical asset. This connection allows for two-way communication between your physical and your digital systems. Now, within digital twins, there are two main types, system level and component level. System level digital twins are when you have one complete digital twin to represent your entire system, whereas component digital twins are when you have a complete digital twin for each component in your system. Now, when you have each of these digital twins, you can then interface them to account for any component interactions. Within the literature, there's a lot of work towards component digital twins because they do allow for greater modularity and scalability. However, they do come along with the complexity of having to couple each of those digital twins, but that is a research gap that this work is trying to put efforts into closing. Now at UGK, we have a system we call the tri-twin. This is a PWR-like system. Now you might ask, if your main goal is advanced reactors, why a water system? Three main reasons. One, this system is easily accessible to us and allows us to generate real-time data. Real-time data generation is a really important aspect of building complete digital twins. Two, there's another group at UTK working on building the system-level digital twin. For this system, this gives us the really unique opportunity to do a comparative study between the component and the system-level digital twins. And lastly, the main goal behind this framework is to make it transferable. Now you might ask now, okay, well, what does that framework look like? This is what we've developed. In the middle here, you'll see our runtime infrastructure. This works like a data bus. Going into it, you have your real-time sensor data coming from your physical system. And at the top, you'll notice nodes. Each of these nodes represents a component within your system, and then each of those nodes is that complete digital twin for that component. The nice thing about this type of framework is if you want to make a change to one of these components, you can just focus on that digital twin rather than having to deal with the system level code. Additionally, if you want to add a component or remove a component, this type of framework makes that significantly easier. Now, of course, if you have different types of systems, the components you have are going to differ. But the idea behind this is that the skeleton of this framework can remain the same, whether you're doing advanced reactors like MSRs, or even nuclear fuel facilities like the Uranium Science and Technology Center at Oak Ridge National Laboratory, in which this case, instead of having components as each node, it would instead be each of your chemical processes. Now, if you're interested in learning more, you can check out my recent poster. And while this work is still in its early stages, we see it as an important step in helping close the gap of component integration within nuclear digital twins. Thank you all for your time, and I hope you enjoyed.